in all right. Um, I am Fabian Fernandez. I'm a professor here in the Department of Soil, Water, and Climate, and we're just so thrilled to have all of you here. Um, let's see here. Okay, we'll advance it this way, I guess. All right. So before we get started with the program today, I would like to express appreciation to the both the Larson and the Allmaras families, and I would like to introduce some of the members of the family that are here with us. And please just wave your hand as your name is read, so that people know who you are. We have John Allmaras from Oklahoma. She's Ray's daughter. Mary Allmaras from Colorado, also one of Ray's daughters. Anthony Allmaras from University of Nebraska, and Ray's grandson. And he is with Jessica Olson, also from University of Nebraska. And she's been upgraded to from a friend status to a girlfriend status. She came last year. So welcome, and it's great to have you back. Um, we also have Lorraine McMahon from Minnesota, Ray's sister. Um, Camille Lex from Minnesota, Ray's sister. Wonderful. Patty Stradley from Minnesota, Ray's sister. She's not here, okay. Mike and Jan Stradley from Minnesota, Ray's nephew. Mary Pat McMahon from Indiana, Ray's niece. Wonderful. And George Menmon, sorry, I've been reading this wrong. Menmon from Minnesota, Ray's nephew. Thank you. All right, and then we have also family members that are online, and they were not able to come, but they were able to arrange their schedule so that they can participate. And I really appreciate all of them here and the ones online to take the time to honor Ray's um, legacy. So the following are online. Modesta Almaras from Washington, Ray's spouse. Kathleen Almaras from Washington, Ray's daughter. Steve Almaras from Washington, Ray's son. Pauline Adamu from California is Ray's daughter. And then two son-in-laws, Rahim Adamu from California and Mark Hauser from Oklahoma. And then we have also four grandsons present online. Paul Hauser and Carly Watson, Scott Madeline Hauser, Rashid Adamu, and Razak Adamu. Did I mention everybody? Did I forget anyone? Like I say, wonderful support from all the family members. And are there any from the Larson family that I forgot to mention? All right, well, let's give them a big hand. We also like to thank Ray's family for the support that they give, not only to this lecture, but also to the Raymond Allmaras Endowed Professorship and the Ray Allmaras Graduate Student Fellowship. This support is really a wonderful help to the department, to the students, to the faculty here. So thanks again for your support. Let's give them a big hand. So this lecture series started back in 2003, and you can see there the different speakers that we have had over the years, a great list of speakers. And this lecture started to, highlight the research and the cutting edge work that is being done in the area of soil and water, and also to recognize bills and raise contributions to the science, and to kind of preserve their legacy, and also continue to look at the emerging issues related to soil and water specifically. And we have a wonderful list of speakers there, and today's speaker will be no different with Sylvie Brouder. She will be introduced a little bit later in the program. Now, to put this program together, there are a lot of hands that are behind the scenes helping us, and so this collective effort of people is what allows us to have wonderful topics and wonderful speakers every year at this lecture. I will mention the different committee members. If they are here, you just kind of wave your hand. Paul Capel from USGS and Civil Engineering. Brent Dalswell from USDA ARS and also in our faculty or in our department. Diane Carwen from Forest Resources. Joel Larson from Water Resources Center. Lindsay Pease from our department, Carl Rosen from our department, Gary Sands from Bioproducts and Biosystems Engineering, Jeff Strack from the Southwest Research and Outreach Center and also our department, Melissa Wilson from our department. And we also have members that are not necessarily part of the committee, but they are the ones that really make it happen. So Rachel Mathis here, she is the one that really orchestrates a lot of the behind the scene things. And she was helped by Carrie Jargo and Nicole Smiley. So thank you all for your help. Let's give them a hand. All right. Next, I would like to invite our Dean Bird, to give us a little update on the college. And then after that, we will ask Brent Williams, our department head, to give us an update on the department.
All right, thank you, Fabian. And first off, certainly want to welcome the Allmaras and Larson families with us today. It's terrific to see you again. You know, you've been doing this a while when you recognize people after you do 100 of these a few times over, so welcome again. And it was like a bait for next year's event to see if there's a marriage or is there something else going on here to get a riff on that. So we got to come back again next year. But it's delightful to see everyone again here at this lecture series. I have been doing this quite a few years now. And just want to talk a little bit about the importance of soil, water, climate in this work, of course, and the growth that's happening here and other places across the college related to this. Before I do that, as was mentioned, Brent Williams, one of sort of in the news front, of course, which many of you, he may be old news already. It doesn't take long to break someone in, but he's been here about a year now, completed his first year as the head of soil, water, and climate, which we're excited about. He's been doing a terrific job. I know, working with faculty, he's talking to faculty about what their goals are, how the department moves forward. So really appreciate that. And you see him sort of sitting there sternly. And then I look a little bit to his right, and here's Carl with a sweater on. He used to wear suits to this. I know she's wearing khaki pants. Look at him smile and laugh. It's like, you know, it's like this, this entire weight's been lifted from his shoulders and shifted over to Brent. But we certainly appreciate all of Carl's work with the department over time. And I know we just had an event a couple weeks ago at the Sam Plain Research Farm. I'll talk about a bit, but is really enjoying, I think, getting back into his work as a researcher and teaching again. So appreciate that work. And that's one of those things that, you know, we talk about those, what seem like minor appointments, but they really do start to shape the future of programs and departments going forward. So we appreciate that work. And then, of course, I want to welcome Dr. Brouder. How close was I? Close. So I'm going to ask her to pronounce my name now. Nobody ever gets that right either. But certainly coming back to appreciate you coming today. I actually did watch, which is the beauty now of having speakers coming, go watch videos they've done somewhere. And it was one on the carrying capacity of Earth and the potential for that in a series, but it was an excellent presentation. And I apologize in advance because I am going to have to leave before you're finished. So I just wanted to let you know that I apologize for that. It's only because I'm scheduled a little bit too heavily for Friday afternoon. So, but thank you for joining us. I'm sure we'll be delighted to hear your remarks. Back to soil, water, climate. I mentioned one thing already. There's quite a lot going on. One of those that's really exciting is Minnesota Climate Adaptation Partnerships. That's being led here through soil, water, and climate. And a second side of that is an AI climate initiative. And of course, Heidi Roop is leading one of those initiatives. And then another initiative is the AI Climate Initiative, which is a partnership with NSF. It's through with the College of Science and Engineering. And Dave Mulla, who I don't see here, is one of the leaders on that project. And I bring those up a little bit. I'm not, I love to go through all the projects, but as you all know, anything we talk about today involves soil, water, and climate. It is at that central piece of, are we going to the Earth's carrying capacity, be able to sustain that? And one of the best lectures I ever saw on that I actually do watch it once in a while. Nick Jelensky's not here. He did a TED talk related to soils and what that and how that relates to humans and our existence, our very existence. As we're looking at some of these changes that are occurring, we are thinking about this as our existence again, again, as if we ever stopped, or more awareness related to that. And so really thinking about those elements in this process. We've certainly made investments in this area, although it's somewhat indirect in some ways, seen as this. I mentioned the Becker Sandplain Research Farm. We sort of took the Becker off, but it's still the Sandplain Research Farm, which we just opened, was this 2 weeks ago, 3 weeks ago? We opened that up. It'd been there for a bit this spring. And the key part of that is some of the work that's been done here. Vasudi, your work in precision irrigation, potato research going on there, kind of looking at the diversity of soils and characteristics, water across the state, and how we manage that more effectively. And that investment is helping to support a lot of that work going on here as well. So those are just examples of that work that's occurring in soil, water, climate that continues to be at the bedrock. I guess that's not soils, right? Of everything we do in that work. Just a brief, kind of broaden this out a bit. The university, of course, this last year, if you've been watching the University of Minnesota, one of our elements is President Ettinger came in as interim president a little over a year ago now, as President Gable moved towards the University of Pittsburgh, where she's currently president. And so just this last spring, we completed a search for our new president, President Cunningham. She'll be joining us here very shortly at the University of Minnesota. She comes to us from the University of Michigan. So certainly from a premier institution, her background is in medicine. And we're already starting to have conversations. She comes on board to talk about the work we do here in CFANS, the importance of that aspect of where does everything from soils to plants to animals, certainly the nutritional side, how does it impact human health? And as part of that, fortuitously, we're starting a new project in southern Minnesota in Mower County to name pronunciations. It's like, for those of you from Minnesota, Hormel's in Mower County, but it could also be Hormel in Mower County. We're not sure which. Because nobody pronounces all the same, but it is in that county, and it's really an integrated system by design, looking at everything in the cycle of food, agriculture, soils, human health. The Hormel Institute is there, which does research on cancer research. That's over a couple $100 million investment to try to draw together this issue as we look at our environment for agriculture, the consequences of production agriculture, how we're going to sustain our soil resources, our water quality, those resources, and actually get to the point of being able to look at that as a complete cycle, including energy cycles, carbon cycles, by design with sensing technologies. We're doing a lot of robotics piece. And just this week, several of you came to a session where we had some of our planning. We're in the pre-design stage to move that forward, to think about how we structure that and getting that right so we can serve Minnesota and the world, which is our ultimate goal, taking the work that happens here in soil, water, and climate, other programs across the college, and bringing it out to impact some of these really great challenges we've been talking about here. So with that, we do have our graduation coming up next weekend, which is just bizarre to me that here we are, end of our semesters here at the end of April, going quickly, but we're certainly excited about that coming forward as well in terms of students. We have about 400 or so undergraduate awards, about 75 graduate awards that will be coming out, or commencements that will be occurring this year. So we're super excited about that as part of this wrapping up the end of our semester. So with that, I will pause my remarks. I believe I'll turn over to you, Fabian, or to Brent, and welcome Brent. And thank you again. And thank you again for joining us today. So.
Thanks, Brian. Let's see. Is it all in the same slide deck here? All right. Yeah, well, this is me, Brent Williams. As you've already heard, I'm the new department head here in soil, water, and climate. My first Larson Allmaras lecture, but I've been hearing about this since day one. actually since my interview before I was even hired, hearing about the importance of this. So it's great to be here and great to meet a lot of the family members so far. And yeah, that is exciting. We get to see, you know, we have our own celebrity couple now that we can track over time. We're going to expect updates, you know, this big annual update, but maybe you could start something on social media for us. I don't know. I'll also add to Brian's comment, our new president is coming to us from Michigan. We found out yesterday our new quarterback for the Vikings is coming to us from Michigan as well. So Michiganders are coming over to Minnesota. So this is our department, Soil, Water, and Climate. I wanted to show this image. This was an image made from an undergraduate student. And we are in the process of making t-shirts with this design on it. So hopefully in the near future, we could have this open for folks to be able to get our new logo on a t-shirt. I'm going to highlight just a few kind of major things from our department this year, updates. But I definitely, you know, given the nature of this lectureship, I want to give an update on our foundation funds. And this slide is specifically for the annual student awards that go out, and this supports students for things like travel or other study expenses. So I wanted to just share this. I'll highlight a couple. The Allmaras Graduate Fund supported Demi, and a newer one is the Satish and Cynthia Gupta Fund. Since Satish is here, I'll highlight that one as well. I also want to recognize our other foundation funds that don't necessarily go specifically to the student side, but support our faculty and research and other endeavors in our department. So they're listed here, but I'm going to highlight a few. For obvious reasons, we have the William E. Larson and Raymond R. Allmaras Lecture Fund, which is what brought us all here together today, supporting this. We have the Raymond Allmaras Professorship. We have a William E. Larson Professorship. And I'm going to highlight our newest fund here that's currently being set up is the Edward Landa and Judith Johnson Fund. Ed Landa was a graduate of the department in 1975 and has worked over in Maryland with USDA for most of his career in biogeochemistry, and they're in the process of setting up a fund currently, and I believe Ed is joining us online today, so I wanted to give a acknowledgement to Ed. Okay, so a few other highlights across our education and research. I'm just going to highlight on our undergrad education side in our department. The Environmental Science Policy and Management ESPM program is one of our undergraduate programs that we contribute a lot of teaching to. It's an interdisciplinary one with several other departments in the college, but it is now the largest undergrad program in the college, and has new co-coordinators directing this program, one of which is Soil, Water, and Climate's Nick Jelinski taking over leadership in this program. So we're really excited about it, and there's lots of great conversations going on right now. Actually, just before I came down here, we were talking about the future of the ESPM program. We have our soils minor has grown a lot over the last decade and remains to be a really successful minor program that Nick has been spearheading. We have a new minor that's being proposed with precision agriculture, which is something University of Minnesota has a long history of, but we haven't had specific programming in that for a long time. And so Yushin Miao in the department is leading, bringing that back as a minor. And we're also reimagining our other minors in international agriculture and water science, led by Carrie Wolf, and climatology, led by Tracy Twine. Our research is going quite well. We have a lot of research funds coming in through our department. I'm not showing the figure here, but per research appointment, we're well above the college average, and we're doing really good on the research side. And I'm just going to highlight a few of the large-scale projects. These are all multi-million-dollar projects that have come in over the last year, or have grown a lot over the last year. And Dean Burr has already mentioned a couple of these. The University of Minnesota Climate Adaptation Partnership, or MCAP, being led by Professor Heidi Roop, has grown extensively, and they have a new a new home base just in the building next to us, McNeil Hall over here, and have done a ton of hiring and also are hiring throughout the state for climate adaptation, climate resiliency sort of efforts. Dean Burr already mentioned the AI Climate Project, which Professor David Mola is leading the CFANS part of that project. And I'll just mention that David is the Larson chair. Heidi and Tim Griffiths are also a part of that project from our department. There's a large USDA project that was just sponsored, $7 million project to put tall tower greenhouse gas monitoring network throughout the middle of the US. That's being led by John Baker, who is with our USDA ARS group here in our department, and Tim Griffiths. And then lastly, there's a new NSF engine program who Jeff Strock from Southwest Rock and faculty in our department is a member of this. And this is a very large, the core project is something like $160 million. Jeff doesn't get $160 million. Unfortunately, I think we all wish he would, but he gets in on that project. It's Great Lakes looking at circular blue economy. Couple announcements on new faculty members. So Vasu Sharma is a tenure track assistant professor now in our department, which is a change from last year at this time. And she's extension research position, doing water management and water quality. Vasu is already well connected throughout the state and is sort of a co-collaborator on almost all of our projects right now and all of our new proposals going out. So she's very busy and stays cool and collected throughout all of it. So it's been fun having Vasu. And this is the first time publicly announcing this, but we have another new tenure track assistant professor, Dr. Peter Neff, who's over here. His position is a teaching research position, and you'll find him in Minnesota part of the year, and you'll find him down at the South Pole going around Antarctica, digging up deep ice the other part of the year. And if you want to learn more about Pete, Icy Pete, you can find him on all social network platforms. Has quite a following. A few faculty awards to highlight. Professor Heidi Roop received a distinguished McKnight Land Grant Professorship this year, which is very much an honor. Also an Extension Distinguished Outstanding Leadership Award. Dr. Yushin Miao received the Tsingtao Agricultural Science Award. Fabian Fernandez received the Diversity Trailblazer Group for the Soil Science Society of America Presidential Award. And Carl Rosen at the SSSA meeting this last fall delivered a very distinguished lecture there, the Leo Walsh Soil Fertility Lecture. And Carl also was honored with Lifetime Membership Award from the Potato Association of America. So he is our big potato, as I've mentioned before. And I definitely want to also, as Dean Burr already said this, but I want to acknowledge Carl for his 13 years of excellent leadership and service in this department. And every day I see Carl, his smile grows larger and larger for not being there. A few just last short things. We have retirement in the department. Jay Bell has been in this department since 1991. His research is in pedology, wetlands, and peatlands. He previously served as CFAN's Associate Dean of Academic Programs and also Faculty Affairs. Broadly, I say Jay is a wonderful educator, and he may not say this specifically, but he is a historian. Not by training, but by interest and by learned skill, very much a historian. And it's been, I only got to overlap here with Jay for a year, but it's been very much an honor, and Jay's back here. I want to recognize you for all of your service. And you probably noticed I dug up some old images of you online. I believe this is you and your grandfather on the family farm, which has been in the family since the 1600s, something like this. We lost two past faculty members in this last year, this last summer, and then more recently. John Moncrief passed away this past summer. John worked in soil conservation, soil erosion, and compaction, and later in his career, more in environmental quality. And George Ream passed away more recently, and George was very much a leader in extension programming and in nutrient management in the state of Minnesota. And I've heard that George was there for the farmers and for the people. Everything else kind of came second. So these are two big losses, and hopefully they're somewhere having a great conversation today, or watching this great lecture maybe. Today, the University of Minnesota soil judging team is wrapping up their national competition in Iowa. I didn't hear results yet. They were announcing results at some point today. But this is one of our largest things that we try to support and raise funds for every year. This is a great program that really gets students hooked on a lifetime of thinking about soils in great detail. So one last advertisement is every Wednesday, we do have a lecture seminar series. It's available online now. If you want to connect with that, Rachel Mathis, you can find her online as well on our department website, can add you and get you to the Zoom links. Also, if you want to support the soil judging team, we're always looking for extra support for their travels. They travel twice a year and have a lot of expenses, so we're always looking for extra support for them and that great program. And I think that's all I have. I'm going to hand it over to Fabian here. Thank you.
Well, it is my great pleasure now to introduce our guest speaker. Dr. Sylvie Brouder is a professor and Wickersham Chair of Excellence in Agricultural Research in the Department of Agronomy and Director of the Center for Global Food Security at Purdue University. Her research addresses nutrient stewardship in agricultural landscapes and application to emerging digital tools and novel statistical approaches to improve data use for evidence-based recommendations and policy in a changing climate. Sylvie is a fellow of the American Society of Agronomy, ASA, and the American Association for the Advancement of Science, AAAS. And recently, she served as the president for ASA, where she worked to advance an array of open science and data initiatives. She currently serves on the Standing Science Advisory Board of the U.S. Environmental Protection Agency and recently chaired an agricultural subcommittee panel on biosolids. At Purdue, Sylvie oversees all research activities at the Water Quality Field Station, a long-term in-field laboratory, and Purdue Core Facility. A common theme across several of her projects is synthesizing new research data with legacy and private data into recommendations and their framework. With colleagues, she develops and co-teaches systematic review of agriculture and the environment, a hybrid graduate course synchronously taught at Purdue University, University of Wisconsin, The Ohio State University, and Iowa State University. And above all of that, for me personally, she's a great friend, mentor, and scientist. She was my major professor when I was doing my PhD at Purdue University. So for better or worse, the reason I'm here is partly she's blamed for that. So, and it's my pleasure to introduce Sylvie. We are really looking forward to your talk today. So take it away, Sylvie. You can flip it on somewhere to be fine.
Yeah, I'm not sure I have anything. Maybe it'll. See if that works.
Perfect.
Does that work? Can you hear me? Okay, great. It is a pleasure for me. I really appreciate the invitation to come here. It's a great honor. Fabian, we always called him Fabian. So if I slip and refer to him as Fabian, it's the same person, was a wonderful student, very, very diligent, very hardworking, and very efficient at undertaking the research that he wanted to do to achieve his science goals. So it's wonderful to see him flourishing here, and clearly he's flourishing. I haven't been to the campus here in a long time, and seeing George Ream's picture, one of the first times I came to campus was with the soil testing extension group that used to meet once a year. And that year Minnesota was host, and we had a picnic at George's place. And George was very kind to me. I was the first female to join that group of soil fertility extension specialists. And they were nice to me. They were quite paternal. They didn't know what to do with me, but that was okay. I needed it. I really did. And the thing I remember about George, which really stunned me, was that he got tenure, at least this is a story, at Iowa State. And then he gave it up to start all over again here. So it must be really something here to be willing to do that, because to give it up and start again is something that is quite unusual. All right, so I have been working for a long time in the area of nutrient cycling, soils, carbon, nitrogen cycling, other nutrients to water, and I'm an ecologist, so I work on, my degree is in ecology. I work on both the environmental side of things, but my role at Purdue, I am an extension specialist as well, so making recommendations for farmers has been part of it all along. And so this question of why do we have science problems, and why is the public frustrated with the science that we produce, and occasionally or frequently saying, but it doesn't work on a real farm. And so that BMP, if you're not into the lingo, that's a best or better management practice. Why doesn't that practice work on my farm? That is a persistent question. It's been there for years and years. I think we have a certain level of uncertain public distrust perhaps of science right now that has a whole lot of factors going into it, but we have to deal with it and move on and do our best, do our science, and then make sure we are doing the rest of what it takes to make our science usable, because what we do in the beginning isn't necessarily usable. But when I was reflecting on what kind of problems do we have, well, as scientists, we are curious people, and science is fun. But sometimes we invest ourselves in doing things that seem just dumb or seem trivial. And sometimes there's a good reason to do that. Sometimes there's a really good reason, because everybody thinks it's a good idea, even though you have the knowledge that says this is a bad idea. So you have to do the science anyways. But sometimes we're just, curious, and we want to do stuff, and we're not necessarily surprised. And what we do is occasionally people will look at it and after the fact and laugh at us. And sometimes that doesn't do our reputation any good. I put the Ig Nobel Awards up there. How many of you know what the Ig Nobel Awards are? Yeah. So there's the satirical side of me that would relish winning that award. The public service side of me makes sure that I will never be a candidate. But I went back and I checked who's gotten that award lately and what has it been for. And there was a group in the geology area that were given the award for proving why geologists like to lick rocks. And I thought, okay, that's good. And then I went further back, and there was one I liked even better, and it was in biology. And it was a group of scientists who proved that if you tied a stick to the tail of a chicken, you could make it walk like we think a dinosaur walked. So, we do stuff, and maybe there is an underlying reason. And that sometimes gives the public the perception that we're not quite doing the right thing with their public dollars, and it is public money we do a lot of stuff with. And then there are things that aren't necessarily bad science, or even sometimes it's bad science or sometimes it's good science, but it gets hijacked. And the idea, it takes on a life of its own in a sort of a fantasy land. And then as scientists, we have to decide whether or not we want to say anything about it, because perhaps we're getting a lot of money. And we don't know quite how to deal with that contradiction in our lives and what to do about that. And I would certainly say there's a part of that we're experiencing right now with soil. I'm not a quote soil scientist, but I do love soil. I'm not dissing soil. Soil's fine. It's just that it isn't everything in the world. So if you this Soil Will Save Us. There's a really great article by Amundsen, Kiss the Ground and Make a Wish, Soil Science in Hollywood, where it talks about the need for us to be intellectually honest about the problems that soil can solve in our world and the problems that it can't. And it's a very nice reminder that we have to be mindful of where our science takes itself. And we have a role, even after we put a scientific idea out there and we put some proof out there, in making sure that it stays within its appropriate bounds. Then there's the issue of real or perceived irrelevance. Science is okay, it's just not that useful, or it's not in a state that it's useful yet. And this is just an example of a paper that talks about, and you hear this a lot in the developing world context, that we developed a solution, but we didn't do the research needed to adapt the solution to the local conditions so that those who were intended to do something with it could adopt it. So, we're perhaps not delivering entirely on making our science useful. Then there's the issue of, can scientists actually, in their science setting, ever do something that's really relevant to a farm? Because we're, constraining things, and that we come at science with a whole lot of preconceived and incorrect notions about the situation in which a true farmer operates. And so there's a lot of discussion about that. And then there's the issue of the fact that they're scientists, don't believe them. You have to do it on your own farm and see it for yourself, and then it works. And that's out there too. It doesn't mean that our science doesn't work. It's that somebody's just got to give it a try to see if it's okay. So those are all things that are out there. And then underneath all of this is if you know enough about science, you know that we genuflect to a p-value, a probability value of 0.05. If it is 0.055, it pains us to say that something happened. Nothing happened. And that is a standard that's been there my entire career. And we also, while we're sort of trained to like the null hypothesis, in the scientific method, you're supposed to like the null hypothesis, which is, I did this, nothing happened. We don't actually like that, and funding agencies don't tend to like it all that much either. And then there's the final issue, which I want to spend some time talking about, and that is that what you do or what you suggest somebody do, it isn't always visible. You can't necessarily just go out and see it in action, or somebody can't do it and see it in action right away. And so it's hard to see, and there's a reluctance to do something with it if you can't see it the way you expect it to see it. And so this is an example from Alan Blaylock, and he gave me the slide, so I didn't take it from him to use it for this purpose, because he made this comment to me afterwards. He worked on environmental smart nitrogen for a company, and I'm one of those little, someplace I'm a little dot. I did 1 year of study for him. And this just shows that you have all of these locations where you're seeing whether this product is improving, is improving your yield, your magnitude of yield difference. You're getting the result that you want. And he found that, can I add the pointer? Let me add the pointer. What is it? Pointer options. Okay. And, he found that, well, most of the time he thought it's a good product. We're getting a yield increase, but he had this horrible problem that some of the time he got a yield decrease in these trials that were done. And the conversation I had with him is, what do I say? Because what he hadn't done, and he acknowledged this, was collect enough what we call metadata, data about data, to explain why this happened. He didn't know. All he could say was that it works better. I can't even remember, better or worse when you're east of the Mississippi versus west of the Mississippi. And he was kicking himself because he didn't feel he could go back to the people who'd done the studies, including me. And I probably would have said, I can't get that for you because I don't know what I did with it, to get the information to figure out what had happened. But this is not that uncommon in our world working with fertilizers. So this is agritane, a urease inhibitor, which again should help you increase yields, provided you're not putting on way too much nitrogen in the first place. And Steve Evilhar who was in Southern Illinois, and he's looking at corn yields again. And you can see he's got some mostly positive things, but he's got this tail over here of negative stuff. And it's different color bars. So the different color bars are what he's doing with tillage and incorporation. And while it's mostly one thing and not the other, you still have problems when it goes the other way. And you don't want to be on the other end of that phone when it goes the other way, provided somebody knows it went the other way. Because if they don't know, then they're not going to harass you. Okay. So that's looking at yield. But now in everything we're doing, we don't just want to look at yield, which in the world of the agronomic scientist is considered a fairly stable metric. You don't necessarily, if you're running a field trial, you've got your rates or something or other, and you're at your high rate, you'll have a number of replications, but at the high rate, your yields probably will all be fairly similar. And then at the next rate, they'll be whatever they are, but they'll be fairly similar to each other, or they'll be different in a way that we can take out. When you're looking at other ecosystem services, and this is the lingo now for those environmental things that happen in the environment. So it could be water quality, it could be soil carbon, soil health metrics, all these kinds of things. The things in the environment that we want to see improved. We want less nitrate in water because that's bad. We want more carbon in soils. We want more beneficial microbes. We want fewer pests, all that kind of thing. So when you're starting to look at those measurements of these natural attributes, one of the things you find is that those things tend to be much more variable. And so trying to find an average, even when you have reps, is a problem. So I'll tell a few stories. We had a project that was funded by the US Department of Agriculture, and it was on producing together everything: bioenergy, food, feed. We called it our BFF. We were cute. Ecosystem services in the Midwest Corn Belt. So this was about 2015, 2016. And they funded it. Basically, what we were proposing to do is we're going to grow cover crops as an economic crop for bioenergy or for forage value or something like that. And we did the project. I'm not here to tell you all about the project, but what happened was that we ended during COVID. That was bad. But even before COVID, we had problems getting stuff done. We were ambitious, and you have to be ambitious or you're not going to get funded. But we we lost people on the project, people left, blah, blah, blah. So we filed the final report. I'm like, phew, that project's done. And I get an email saying, would you like to come present to a multi-agency group on your project? And I'm like, okay, this has never happened to me before. What the heck is going on? Well, this notion of using a cover crop for something was part of it. And so I agreed to give them a presentation via Zoom or whatever. And we went online, and we were a little nervous because we really did overpromise. But again, I'll say that's kind of what you do to get funding, I'm afraid, is you overpromise and then you try very hard to figure out how you're going to deliver on most of it. So we had, so this field station that I run, we have all kinds of instrumentation. We can measure greenhouse gas emissions. We measure water flow volume from the tile lines. We collect the sample. We measure everything in the lab. We do compositional analysis on tissues. We look at soils, blah, blah, blah. And so we had this big suite of things that we said we were going to analyze and they're related to ecosystem services, and they're, it's not just total carbon and nitrogen in the soil. We were looking at greenhouse gas emissions of nitrous oxide, CO2, methane's not that interesting. And then we were going to do all these biological assays of stuff that happens in the soil. And we started our presentation with the stuff that, okay, let's start with the stuff that we can explain, that's easy, blah, blah, blah. Okay, so here we're looking at, can you grow corn after a rye crop that you grow to a pretty large volume? So you have enough volume that if you had an ethanol market for biomass, you could sell it and get an economic value. You could ensile it. We had Cura clover, our early years of maize yields with Cura, not so good. We found out just recently, if you almost kill the stuff, you can get a maize crop. I'm not sure how much of a Cura stand we'll have this year. But so then we're like, okay, and then we have to talk about things like measuring water quality and what can we see relative to our objectives. And so I showed them this because we have measurements. What we do at the field station is we'll get an idea for a project, and we'll modify a couple treatments out there. We've got 12 options of replicated treatments that we could change to something new. And in this case, I'm talking specifically about adding this rye as a cover crop, winter rye as a cover crop, to harvest for biomass. And so what I started with was, okay, here is since 1995, this is what the different corn soy systems we had out there that we were using in this study. This is what the nitrate concentration looks like. Okay, bounces all over the place. And what I really wanted to show them was this. I took out in that figure over there, I have these little error bars which show the variation across the replicates. And I took them out so that you could actually see the stuff, because if you look up close, all you see is error bars. And to show that, okay, well, we still have, we had a couple years at that time of rye, of also Cura, although it took longer to get it established. And you can see, okay, yeah, we are seeing a trend downward in our nitrate right away. And we would expect that to be a significant difference. What the whole group absorbed was not what we were telling them. The thing that occupied them from the moment we stopped talking was the amount of variability that we have here year in, year out. And they were just like, oh my, how can you tell anything from that? What is going on? If you have that much variability, how can you monitor that on farm and know what's going on? Well, that's that's an important question. You can't, some of these seems to be, sorry about that, some of these seem to be reformatted a little bit. When we're looking at these climate smart ag practices and these targets like soil carbon, we are looking for things that where small changes matter, but the variability in those, in the measurements and in reality, in those quantities of stuff across the landscape is likely to be very, very high. So you're looking for a change in something that's inherently very, very, very variable. And that makes it really difficult to see. The USDA said, we had this conference back in 2017 that they funded on, it was a big discussion of whether or not we were, the science was ready to have structured payment programs around ecosystem services. So payment for agriculture pages was payment for agricultural ecosystem services. And we brought in people from all over the Midwest especially, but also to talk about this question of ecosystem services and what we could pay for. It was economists, you know, how would markets and policies be structured? And the consensus of that group that we convened, about 50 to 60 scientists, was that science isn't, you can do it. You probably can't measure it on every farm for some things like phosphorus and stuff like that, but science isn't there yet for assessing carbon. Well, where are we today? I mean, it's like, okay, whatever we said didn't make much difference in what we're doing right now as we think about carbon. So at the time, there were statements out there that were just very appealing for those looking for ways to do something other than reduce energy use. So there were papers out there saying that, oh, if you increase the global carbon stock in soils by 10%, we're going to cancel out 30 years of anthropogenic soil CO2 emissions. Okay, so, oh, this is so appealing in a political context. All you got to do is have farmers, not me, somebody else, farmers do something that increases their soil carbon by 10%, and the rest of us can do whatever we want and keep emitting CO2. And that's a really, really powerful measurement, a message. The problem with that is that even at the time, and why we were saying that is, we knew a lot about which practices might do something to soil carbon at all. We knew about the challenge of measuring it, and we knew a lot about the expected magnitude of change and whether or not you could just happen to stroll out into a farmer's field and make that measurement. Nonetheless, we forged ahead. So I'm going to hop back from soil carbon for a second and talk about nitrate again. I know you all have a big nitrate problem. And nitrate in drainage water is incredibly variable to measure. When you have a big difference in a system, the variability matters a whole lot less. You can see the difference. So here, this blue line here is our native prairie system. Almost no nitrogen coming out of that thing. A little bit because soil land mineralizes, it turns over, it can leach, whatever. And then we have various corn, soy systems. And then if you transition them to something like a perennial crop, so switchgrass, we had miscanthus out there. Depending on the lag time, what you see is, you know, here's the prairie down here and switchgrass, and then these are the other corn soy systems up here, plus transitioning miscanthus. What you see is pretty quickly, you get to a point where the perennials are cleaning up the water, even though in this case, we were adding some nitrogen to the switchgrass and miscanthus to maintain their productivity as we were hauling off a lot of biomass for a theoretical ethanol crop. So effect size is big, variability matters less. If you're looking for small changes, variability is your world. And that's all you care about, because you're going to have to figure out how to deal with that in terms of assessing. When I was initially talking to Fabian, I was saying, okay, we do water quality, we do greenhouse gases, and we do soil organic matter and soil carbon and various soil metrics. And all of these measurements have these challenges. Greenhouse gases, actually, you are looking for fairly small effects, because in the end, it's not that many pounds per acre, kilograms per hectare of nitrogen that you're talking about. But if you looked at greenhouse gas emissions, they're all over the place for good reason. And so they're hard to measure and get this value, this magical seasonal estimate. But I decided I would stick with with water quality, which has the variability issue, and then soil organic matter, which has the variability and time issue, accrual issue. So if we talk about, at the field station, this is kind of a side comment, but I wanted to remember to say it. I've always had this rule of thumb that if you want to do something out there, you're going to need to find some funding because it's expensive to do stuff out there. We'll help you. But you've got to hold a treatment in place for 5 years to be able to get the value out of the facility. Mind you, I hadn't analyzed the data to be able to say definitively, but 5 years, why? 5 years is a typical USDA linked project, so get a USDA project and we'll do some stuff there. We do pilot stuff for people all the time. So over the years at the facility, we've looked at water quality and nitrogen. We've looked at manure and E. coli movement and hormones and antibiotics. Then the funding world shifted to being concerned about sea sequestration in the first iteration around 2005. We did a lot of that work. And then we moved into, everybody wanted to know about greenhouse gas measurements. We did some of that work. Then it became bioenergy, which I've just which I was talking a little bit about with Ms. Canthus. And then we went into co-production of ecosystem services, and we're still kind of there right now. So let's look at this nitrate data, because there's this issue of how big of an effect are you looking for? And then, you know, can you see it? So this question we have had out there for 23 years. We've we've kept up with the corn hybrids and changed hybrids and stuff like that. But we've had a system of continuous corn without rotation at 100 kg per hectare and plus another 20 or so, so about 200 kg per hectare. We've had a corn soy rotation also with pre-plant. Those first two would be considered, well, it was considered at some point a while ago conventional management. I'm not sure where it is now, but they are controls. And then we had a corn soy rotation where we just reduced the N rate by a little bit and we side dressed. So we waited longer, we reduced the rate a bit, and we, okay. And so 23 years of these treatments. So what do you think? Which one is going to be the best for water quality? Any thoughts? Continuous corn, is that going to have more leaching? Is that going to be worse for water quality? We don't like monocultures. Yeah, maybe. No, you guys in the back are nodding. Thanks for playing. Okay, so you think that the side dressing and reducing, is that going to result in a reduction in nitrate? Okay, nodding. Okay, all right. Thank you. Okay, so what happens? So here's what happens. So what you're looking at is, this is what's called a forest plot. You're looking at all the years. And you're looking at simply the difference between the side dress versus the pre-plant in a corn soy rotation. And you can see that it bounces around a bit. Some years there's no difference in nitrate concentration. Some years it's, most of the years it's either no difference or it's a little bit lower, right? And at the bottom you see, on average, you get a rather small reduction in nitrate concentration. It's not that, it's probably about 10% reduction in when you go to a side dressing with just a modest reduction in fertilizer. And the change happens right away. So this just shows you the calendar year of the study, and that effect is happening right away. You just can't see it because we just don't have, well, we can't see it at 0.05. We don't have enough statistical power. How long does it take to get to 0.05? But in this case, it took about 6 years to get to that level of significance. So we got 4 reps. It takes us 6 years to see that small effect size. That's the reality of that kind of measurement. So now you say, okay, I want to go see something that's going to make a minor impact, but if minor at scale might be important. And I want to see that change, and we'll get to the soil carbon thing in a second. So it's gonna, I cannot, as a scientist, expect to see that effect. I can't see that performance if I go to a farm. Even if you had a side-by-side comparison, which most won't, you're just going out there, you're measuring one year, you're measuring another year. They started doing this practice, and now the nitrate concentration went up. Yeah, maybe. It doesn't mean that if you had had a comparator and enough replications, you would see that it went down. You just can't see it. I see Mike Schmidt smiling back there. Okay, but wait, it's got soybean in the system, right? So both of these rotations have soybean. And if you want to know what happens with soybean, well, it actually makes the effect smaller. That's because soybean fixes a lot of nitrogen, and then you haul off the yield, and you leave a lot of residue in the field, and that residue mineralizes, and that residue can run away. And in the end, you're just about almost at the same spot. Darn. And in this case, when we're comparing these systems, it seems to take only 3 years, but we have both, there are 8 reps involved. So it's the same number of comparisons that you need to see the difference. Okay, how does continuous corn measure up? This is just, I show this because continuous corn is not always evil. There is absolutely no difference between the continuous corn with pre-plant N and the corn soy rotation with pre-plant N with respect to the water quality. It's average, oh yeah, I didn't, but you can see the number, it's going back and forth. It's all over the place, right? Why is it that way? I've looked at a couple of things. Is it a high yielding year versus a low yielding year? Is it whatever, right? Is there a pattern to that? I don't know. But anyway, in general, the reality is, sorry, it's not that bad. It's not, the monoculture itself just isn't necessarily a problem for water quality compared to just a corn soy rotation, which some would say isn't really a rotation. It's just another monoculture in our corn belt. What about impacts on yields? Well, the yields for the continuous corn were a bit lower, and that would be expected because of a lot of things, including, in theory, pest pathogen, whatever, although there's no, the time to see it is long. The yield differences are bouncing around. So it takes us a long time to actually see that difference. Sometimes it's really up, sometimes it's really down. And we don't know whether, are our N rates correct for either crop in terms of a 1-to-1 comparison with an N credit for soybean. I'm not going to go there right now. In terms of the side dressing, there's no difference. And there's a trend over time that the difference is actually getting smaller. So, it does something to reduce, but it's a very modest reduction. And when you're interested in cleaning up water by 40%, not 10%, but if you're interested in 10% plus 10% plus 10%, you could start thinking about stacking practices or whatever. So when where we are in Indiana right now is that we're actually interested in, we don't have a nutrient reduction. We're a state without a nutrient reduction strategy right now because we haven't been pressured enough by anybody to have to put one together. But now we're in the process of putting together our state nutrient reduction strategy. And so we've been looking around, and we're trying to figure out, how do we extend this to how do you extend one study to Indiana? That's always a question. What can you say about an entire state from just one location in the state, which has really different soils? And that's the big key. It's got really different soils. It's got high organic matter soils, which aren't necessarily typical of the majority of the state. So we've been looking at other states, and we picked Iowa as a model. Jane Frankenberger is leading this, and she works a lot with Matt Helmers at Iowa State. So she was interested in modeling our approach on Iowa. And basically what they do is and I think it's similar here, as you look at all the different things that one might do with either nitrogen management or land use management or other factors, and then assign and see, look at the science, figure out what % reduction you get with that, and then is there an impact on corn yield? And that's what we've been trying to do. This issue, we talk about the 4 R's in nutrient management: right rate, right source, right time, and right placement. And rate is a big one. Now, if everybody is already applying a recommended rate and the recommendation is good, then you may not have too much to gain by just saying apply the right rate. We'll get back to that question. But I got stuck thinking about the rate category because I have looked at rates, and that was Jane wanted me to look at that. So the challenge is that when we're trying to look at measured concentrations in drainage water and the management practice itself, there are not that many places in the Corn Belt that have facilities where you can study this question. Minnesota does. Iowa has a couple, Illinois, Missouri has a couple. So you're looking for, okay, what did they find, and is it relevant to our climate, our soils, or whatever? And and a big problem is that these studies tend to have low statistical power. They have a few reps. We don't have 30 replicates in a given year. So it makes sense to try to put studies together with other studies to get that statistical power. Jane came to me because they had gotten this far, and that is they had taken studies from Iowa and, well, from around the Corn Belt, and this is loads, not concentrations, and they had plotted them out. And if you know anything about statistics, that's a zero relationship. And it's really zero. The R squared, you have no business taking this and trying to make a solid science statement about that green arrow, that change. That's just, if you can hope for that, but that's not what these data show you is happening. Okay. So I was looking at it. All right. And that's what they really want. They want to know what happens if you reduce the rate from a high rate on a farm to just the optimum, the economically optimum end rate. What's going to happen? We're not asking people to sacrifice yield. We're just asking them to be reasonable. And so that was the little space that they were interested in. And the problem, there's no relationship at all. But there's tremendous variability here. So how do you deal with that? What do you do? Well, there are things you can do that are out there. Another problem that I don't want to not acknowledge is that different states have different ideas of what the recommendations regarding the economic optimum. And so this just shows you, I put in red Illinois and Indiana because for whatever reason, we recommend, maybe it's Eastern Corn Belt stuff, we recommend really high rates compared to the rest of the world. And that's an open question for discussion, but this just shows you what are the recommendations for corn soy, what are the recommendations for continuous. Here, how much do they think a soybean crop is contributing? And in general, the way this works, I'm not showing a curve, but the way the curves are fit and the data are so variable that typically the expectation that a farmer will lose $1 either to too much nitrogen fertilizer or to yield loss at the other extreme is about 15 to 20 kg per hectare. So you take that optimum and a farmer could go down from that by 15 or up from that by 15. And in theory, they would only lose $1. But that's a pretty big range for nitrogen. So remember my little study previously, I was just talking about 20 going from that high to kind of the mid, and that would be a 10% reduction. We did, so I was looking at all these data. We were particularly interested, and we decided to have sort of 2 categories of economic optimums, which would allow us to think about the different state requirements. And then we had this high category that we were really interested in, and then because there was an expectation that a lot of farmers were doing that. And then we had very high because we had some observations. And this is what the data look like when you plot them all together in terms of concentration. I didn't show you that before. But you've got, you've still got this high variability, and you can only see in this relationship a pretty small change as you go from very high, from up here down to here. Fitting this curve only shows about a change of 1 ppm. And this is what, I showed you that before, and then here's just a weighted average by the categories, and you're really not gaining anything. You still have this mess to deal with. Well, there's some nice tools out there now, and I have a very friendly statistician that I like a lot at Purdue, and I run everything by, because I'm not necessarily sure I'm doing everything correctly when it comes to statistical meta-analysis and extracting data from papers and combining them. But there's this way of combining papers that don't all have the same treatments, this category issue, and that's what we were interested in. And so I took studies that had, different rates or different numbers of rates, and I combined them all together. And you get this network where maybe you only have 4 comparisons of very high to high, but you have another 8 going to the economic optimum and another 10 comparisons of high to the economic optimum. So you can say, okay, well, I only have 4 comparisons here, but I have these other indirect comparisons, and they should tell me something about the direct comparison. And that's what you're doing with it. And what happens? Well, it turns out quite nicely. You can see that you have so this is combining corn, and corn soy pre-plant applications, because we weren't seeing much of an impact, but I did them separately. We just didn't have a whole lot of continuous corn observations. But what you can see, let me get this up here, is if you're going from very high down to there's nothing here, because everything is being compared to the economic optimum. But you've got about a 4 ppm change going from the very high rate. You've got 1 something going to 1.5, maybe going down to the economic optimum. Other insights that are important to address. These are, I'm giving you we're talking about going from, if you're going from 232 down to 178 or 180, you're getting a lot of benefit. Question becomes, do farmers actually apply that? You get a smaller benefit. Oh, I'm not sure why. It must be showing something different, because it was 2. Oh no, it's 2 between. It's almost 3 if you're going from very high just down to high, which is useful to know. But you still got this problem with it between study heterogeneity, and there are all kinds of other problems. I don't want to go into them in detail, but you can make a general sort of statement. So this is the same thing, and it's just percent reductions. So 25% reduction if you're going from, okay, now we're talking something important. If you're going from very high down to the economic optimum. So then you have to think about who's actually applying very high, and we'll get to that in a second. And then what happens to the yields? So, at least as a starting point, you can go get a somewhat greater than 20% reduction in nitrogen and maintain 95% of your yields. Researchers would say that's okay. Farmers might not like that. Before I go on to what are farmers actually applying, I want to touch back on the story of soil carbon. Check on my time here. Okay. We have been talking a lot. There's a lot of traction for paying for soil carbon. So one of the set of treatments we've had at the water quality field station is a native prairie. Gets no fertilizer, was restored back in 1992. It's just there, and we monitor it as a control. And one of my graduate students back in 2004-05 made total profile C comparisons and found no difference amongst all the treatments we had out there after 12 years in place. So we had had a prairie for 12 years, we did continuous corn, we had corn soy. no difference. There was a little bit of difference in the surface soils, but overall no difference. And not surprisingly, coefficient of variation, very high variability across the replicates. All right, and he had multiple cores per sample, but only 4 reps. So, okay, so back to this. We want to pay for 10%. Indulge me. We talk about in terms of assessment, we know it's got to be the total soil profile, but in reality, what can we get people to test? Let's say the top 30 centimeters. I've seen that number talked about quite a lot. So we're going to have people monitoring the top 30 centimeters of soil. If we take our example, which I agree, it's already a high organic matter soil, you might not expect to see much change, but you might expect to see some. There's a lot of discussion of that. In order to understand the stock, you've got to know what the bulk density of the soil is, whatever. Anyway, we know how variable those measures are. We can take that information and we can say, well, our goal is to increase it 10%. And how many measurements would I need to increase it 10%? Power analysis. What we should all do before we run our experiments, and we never do because we do 4 replicates in a completely randomized block design and we go away. But anyway, so, okay, what does it tell you? I did the bulk density separate from the concentration. Basically, it says I might need about 25 replicates to see that magnitude of difference if it were there. All right, so now I have been measuring for a different reason, the C concentration in the top 30 centimeter soils. And I was like, oh, aha, I can go check. How many measurements do I need? How many reps? So I went back to the field station 20 years after. So if there's a difference, we've been doing these same things for 20 years now. If there's a difference, we should be able to see it. Okay, well, it's there. It just takes all the years of data to see it. So it's hard to see, it's there, but you're looking for a small effect and it's highly variable. Okay, well, I should fully disclose, I analyzed this as a randomized, there is a slight block effect when you take it out. It goes down to, I think, 6 years to see it. So, and we also have a lot of data on the loss on addition routine organic matter measurement. And you can fault that measurement for not representing the C stock correctly across soils. But in this situation, it's actually tracking the magnitude of change pretty well. And by the way, at the soil testing lab, that test is way cheaper. It's part of your soil fertility package at $8 a pop versus a separate test of a whole lot more. There's also the issue in the soil lab. We're pretty careful, we hope. But testing labs are allowed to have variation in their result. So you're going to add that variability into the measurement if you're using a commercial lab. So in the end, we can ask ourselves, if we go back to Guillermo's stuff, if this is a interpretation error. So this comes back to statistics. And I have had a refreshed view of the quote of statistics are used much as a drunk uses a lamppost for support, not an illumination. We use them to support what we want to say rather than to say, oh, aha, I should have had a moment and realized I was making what's called a type 2 error. There was an effect maybe, I just couldn't see it. So, okay, that's the challenge of not being able to see. All right, I'm going to spend the last few minutes, and I know I'm running along here, swapping my high horses and talking about bigger data in ag and what do farmers actually apply. What farmers are self-reporting they apply doesn't seem to even match what we're recommending. So when I say self-reporting, this is to the USDA in their fertilizer workbooks and things like that, where they do a survey, and supposedly there's one they did last year, but the results aren't out yet. In terms of, they did a 2022 census of ag, but I haven't seen, Laura, you're nodding, I haven't seen it yet. I've been checking, but I haven't seen any posted results. And so this shows you what we recommend. And then, so Illinois, we're recommending 200 to 200 plus, and the reported amount for the state was 193 kg per hectare. Indiana, we're probably the worst offender because we're recommending above 200 and then another 35 to 40 for continuous maize, and we're reporting 176. Okay, so this doesn't include manure, but remember this range issue of going from plus or minus 15. So farmers, if we're recommending this and then farmers, this question, are self-reports to the feds accurate? That's what got cut off there. This was a study, a survey done by not the feds, by a researcher who went around and asked people what they're applying in the Midwest. And he broke it out by farm size. It's not a huge survey, but what it shows you is the vast majority of farmers, the orange bar is you can't really read it, but it's 5 pounds or more over the recommended range, which is the upper range of the economic optimum. So you're plus 15, plus another 5, and then a bunch more, especially big farmers, apply plus 10. So, okay, so they're saying that they're reporting a whole lot more. Another study done by a colleague in Illinois, Michelle Wander, kind of found the same thing. She tried to fuse all these different data sources, and she came up with, there's just, most of the states are applying much more. So here we are in Indiana, 92 kg per hectare, more than the crop is using. Now, there's a reason to apply a bit more, but how much more? That's probably not that much more. The problem was that's 2012. The other thing is that she didn't include and applied to soybean, which is in there. And people say, oh, no, that's phosphorus fertilizer, which most of other phosphorus fertilizer is applied in an ammoniated form. But actually, that's listed separately in the fertilizer workbook. And Andrew Marginai at University of Illinois says, no, it's not counted in the N balances. So we have another 40 kg per hectare going on in the fall as ammoniated as ammoniated phosphorus source. So what are farmers actually applying? And I've been banging my head on this question because I was asked to provide insight into a nutrient mismanagement summary for the Food and Agriculture Organization that is looking at all of North America and how are we doing in terms of nutrient mismanagement. And the interesting thing is you can go to the FAO data site and it gives me the N balance for the United States all the way out to 2021. Cool. The problem is, and they calculate it the same way we would. They're looking at fertilizer applied, blah, blah, blah. The problem is you actually go look for those pieces of that individual data, and the data aren't in there. They're estimating them for certain things, but the data aren't being reported from the sources within the US up to either IFA, the Fertilizer Association, or so USDA isn't aggregating from the state chemist's office, from TFIA at the national level. Now, some states are collecting it. Indiana, in terms of survey of fertilizer sales, we are on 2018. We are working on 2018, 2019. So we are way behind. The International Plant Nutrition Institute put a huge effort into developing this geographic information system. They worked really hard on it. It's got a lot of data in it, all these kinds of data. It's a great place to look at balances. I did it for this study. The problem is it stops in 2016. And it's now mothballed as an effort for a variety of reasons. So getting at these data are really hard. You can see, if you look at the end of it, you can see, regions, watersheds going up and down. I should probably show that again. Green is bad, greener is badder. So from 2005 to 2016, California appears to have cleaned up its act. The Midwest stayed the same, or in some regions got worse. You can see the Ohio and then some of them it's published, the Great Lakes got worse. Ohio seems to have gotten better, a whole lot better. I think those data are directionally correct. If you look at the individual years, it seems to be trending upwards, and we're not doing any better. And you can look at other layers there, but it does take into account all of these things, and it really was a major effort. You have to be careful when you try to drill down to the county level, because this is a lot about fertilizer sales as well. So when you see big fertilizer deal or import points, like, I don't know what you guys are doing in the UP, but you got a lot of surplus up there of nitrogen, right? Yeah, well, we do too, right on the edge of Lake Erie. And at first I was thinking, oh, that's right adjacent to our only dairy, except estimates of manure applications haven't gone up at all. So it's about not allocating the fertilizer, and that's really hard to do. Nonetheless, I think this is low-hanging fruit if we're looking at where can you invest to improve this. It's a relatively small database. It's only 11 gigabytes, and it's rotting right now. I contacted Scott Morrell, and I scraped back all of the original files that he had, and they are now sitting in our repository and hopefully being saved. So why is so much data lost, whatever? Is this making data accessible? So this is findable, accessible, interoperable, and retrievable is the FAIR acronym. Is it just too hard? Is it too easy? Why aren't we doing it? In the past, this was a quote, one of my now retired colleagues who was like, I don't want to share data. You're going to scoop me. You can have it when you pry it out of my cold, dead hard drive. That was a note handed to us before we gave a presentation in DC. There are challenges in communicating across disciplines or even communicating across programs. And we have, is that solvable? We have challenges of communicating amongst pieces of equipment. And that hasn't changed. That's been there all along. When we think, there's a really interesting paper that came out recently about how do you make data fair, and what do you need to talk about and do in your community when you do this? And we're really good at step one, where we define who we want to share data. And we're actually pretty good at 6 through 8, where we develop templates, and everybody's going to do it this way, and models, and we think about where we're going to put it up and how we're going to document it. But this stuff here, which is talking about barriers and social aspects of standardization and sources of support to get it standardized, we're terrible. We skip right over that. And big surprise, we're just not getting there. So my feeling about this, we have this huge desire that farmers will integrate on-farm data with research data, or will use farm data to understand what's going on in a research context and make recommendations. They have all these problems with data that researchers have with data. So it's not, you can't just say, oh, look, this comes from our acre farm. These are all the different data sources we have on the farm. And we don't have any budget in our farm budget to manage those data sources. The farm manager is supposed to magically figure it out, and that's not going to happen. It costs money, and we're trying to figure that out. So we've got unique, complex workflows. It's in the lab, it's in the field. The processing, the handling of data is overlooked, extremely time consuming, and there is almost no machine learning way around it. You can't machine learn your way for your data out of your GC in its proprietary software package into a spreadsheet with the data from Campbell data loggers or whatever. There's a touch aspect of this that we have been really slow to recognize. And they have a high cost and a high skill level. This is not trivial. I had somebody tell me who did processing of greenhouse gas data all the time. It's really easy. I can, a monkey can do it. I can train our undergraduate monkeys to do it. She did say that. My response to that is, who's monkey? My undergraduate monkeys are trained to go to the field and take the samples correctly and process them correctly. But if I just walk them in the lab and tell them, do this, that it's going to be a slow learning curve. So we have that problem everywhere. There are other issues with data. I think and we continue. The EPA just gave, they wanted to budget. A colleague called me. She said, I have a PFAS project. They want to know how much money they should give us for data management. And I said, wow, let me think about that. What are you doing? What are you managing? Blah, blah, blah. And I called her and she said, don't worry. They told me they're going to budget 2 hours a year at federal funding rate. I just like, okay, we got a problem. You can't do that. This is not going to happen. All right, and the farmer has issues. We've got a lot of visions. We still think we can magically do stuff with data without getting it cleaned up. And we're not there yet. And we've got this evolution of the tools that we use that's constant, and we're not keeping up. I think getting back to nitrogen is the ultimate whack-a-mole. Unless you're reducing the input and or increasing the output, you've got the same amount in the system, and it's going to be doing something. It's going to be somewhere. And you should be able to find it either leaving or whatever. And we're trying to do this incredibly complex multifunctional optimization. Here we've got things we want to see get better or be maintained on the farm: yield, profitability, soil sequestration, biodiversity, which isn't good right now. We'd like it to go way up. We have things we want to go down. That includes the knowledge intensity, because that's time. And even if you're using AI, it's still human time to make sure you're getting what you want. And when you look at a better management practice, you may not be able to achieve all of that. And I think what we need to do is think harder about the large knowledge gaps, trade-offs, that kind of thing. There are always going to be trade-offs. There's a big people problem. And we need to think about how we deal with the people by the environment, by the management, and the purpose for profit sacrifices that we're expecting them to do, the unexpected outcomes of BMPs. We talk a lot about precision. We don't talk much about accuracy. My goal, it may be a modest goal, is to be, for agriculture and agricultural research, to be accurate about what happens. So there's a difference between precision and accuracy. Precision is hitting something all the time. Accuracy is being generally around the global mean where you want to be, and in the right spot. So we want to be directionally correct, probabilistically accurate at scale. Do no harm. That would be wonderful, but also do some benefits. We do have to trust, and we have to create trust, but we also have to remember to question and police ourselves and not get carried away. It would be good if we had more of an organized strategic framework for agronomy, where we could be more intentional about aggregating what we've learned and building and constantly assembling and moving on. And I think my last point, I talked about it with undergrads, is we know a lot. We don't necessarily intentionally engage in the policy process. I do not necessarily advocate for having to do this, which is giving formal testimony. This is not a lot of fun, and I'm not sure it changes anybody's mind if you've done this before. But there are many other ways which you can engage in policy. And we had a conference in Arizona not too long ago. Bill Hohenheimer from the USDA Office of Climate and Office of Energy and Environment was there. And he's like, you people need to come and meet with us regularly to talk about science and tell us what science can do and can't do, and what we can see and what we can't see, and where we're going to have trade-offs. Open the door, welcomed. I will bring people in. We can have a conversation. We don't do that very often. We're always trying to sell them on something rather than talking to them. And we're always trying to sell them because, I don't know, as a president, that's what we wanted to do. We wanted to get more money for research. So I've taken a bit too long, but I greatly appreciate being here, and I'm happy to take any questions.
All right, let's change the mic. Question. Yeah, okay. So questions for Sylvie, and we do have people online as well. So if you have a question online, please type it and we will read it for you.
Well, something.
No.
That was a wonderful presentation, okay? And even though I'm a soil physicist and you're a nutrient management, one thing that worries me is that you guys are always measuring concentrations.
Sorry.
You're measuring concentration, nitrate concentration.
No, concentration versus load. That's a really
Yeah.
interesting question.
And most of the time when we are talking about cover crops and so on, we are also talking about evapotranspiration losses. And we know if we produce more biomass, there's going to be more evapotranspiration losses and less going into the groundwater or leaching. And most of the nutrient management people, they just don't like measuring flow.
No, so we have all the flow measurements, and the loads are messier, but it's the same effect. We document the load reductions, and basically it's approximately the same load reduction. The reason I focused here on concentrations was that our state group wanted to have us project the concentration reductions that they would then use with USGS estimates of flows.
But from year to year,
There's tremendous.
it's a load that's important because when hypoxia
understand.
develops, it's when we have too much rainfall.
Right. No,
Okay.
I understand completely. but
Okay.
With the load, when you do the network analysis, it's a little bit messier, the variances, but you see the same effect. You get a 9 kilo reduction in load on average across the sites that I looked at.
Okay.
So the load information is there. I was just asked to produce the concentration information for the people in the Indiana nutrient reduction strategy.
Okay. So if it's a load and our climate is changing,
That's true.
okay, and we're getting more precip.
Uh-huh.
So why can't we just say it's not the nitrogen problem, it's a water problem?
Well, it is, but it's also a nitrogen problem.
Well, if you stay within the, why, first question would be, why is Purdue or the Indiana recommending 200 pounds on a
That's
molly
good
soil
question.
compared to when we are recommending 159 or so, okay? The second part is that we are getting a lot more precip, and if you
That's
got
true.
more water going through it, it's going to carry more nitrogen.
That's absolutely true.
And if you take a 4% organic matter in the soil, you got tremendous amount of nitrogen in there. Even if you add 200 pounds, it's the water that's causing the problem.
Last year we saw no yield difference between our 0N plots and our 180 kg per hectare N plots. The season was good. Everybody got over 200 bushels, whether we put nitrogen on or not. So I completely agree with you. It's a load, but the analyses of concentration versus load, when we look at the edge of the field, right, there's not much dilution of concentration at higher flows. So higher flows mean higher loads. Concentration is pretty much the same. So if you reduce the concentration, you're going to reduce the load, whether your flow is high or low, versus not reducing the concentration.
But the point is, if the concentrations have been same, the only way to achieve less nitrogen going to the Mississippi River is to control the water.
Yeah, and we got a lot of water to control and no place to put it. So I understand exactly what you're saying. I am going to argue it is neither one nor the other, both matter. We have done a lot of looking at controlled drainage and things like that. When, you know, our biggest flood events are surface water runoff, probably majority, not necessarily through the profile, because the landscape is flooded out and everything shoots off the surface. And what the impact of that is, I mean, honestly, our facility isn't even designed to look at that kind of movement. So that speaks to needing to look at things at other scales as well, and to downscale to meet. But if you're going to ask a farmer to do something, you could ask them to pull up their tile drains. That might be a little unpopular, but where they have them, you can ask them to plant perennials. There's a lot of discussion around that. Or you can ask them to do things that will make maybe 25% changes in whatever your state level is. I would suspect that, I don't know what your in-state data tell you about what farmers are actually applying.
That's one of the big questions
Yeah,
that we are
my
trying to
husband
figure.
around, and Newell Kitchen took me under his arm and he's like, you know, Sylvie, if I'm a farmer talking to a Fed, what do you think I'm gonna
That's
say?"
right. That's exactly right.
So when you look at a Fed number, you have to have a fairly, and I'm afraid that all that effort going into the self-reports without some other kind of checking on it probably isn't that useful to us right now.
Thank you for the amazing presentation. So I have one question is about, your group did like trend analysis for the nitrate concentration. Did you see or try to minimize the bias of the rain events in the similar dates or 2 days before taking the sample? Because that may add more bias.
Did I try to?
Take in consideration if there is any rain events before, days before taking the nitrate concentration sample.
If there's any rate.
Rain
Oh,
events,
rain events. Okay, these are the concentrations are mean annual. They're means of the daily flow proportional samples for an entire year. So every day there's flow, we go take a sample, and it's caught in a flow proportional bucket. We also have annual flow weighted, where you multiply by the volume, divide back, and have those, and they're actually highly correlated with the average of our annual 24-hour flow proportional samples, like in one case 0.98 or 0.9 at least. So they occur, yes, they bounce all over the place within the year. And, you know, yes, you can see nitrogen went on. Oh, look, there she be, because it rained and now it's in the drainage water. And the higher the N rate that goes on, and depends on the material and the conditions. But we've had plenty of opportunity to look at rain events as a function of time after nitrogen application. I didn't show that. It's interesting. It's just when your goal in this case is to like make a change, you know, in the landscape, yeah, you'll see that. And it is, you know, when you're looking at what the state is measuring and monitoring, they're going to see spikes too. And yeah, so timing matters. Year-to-year variation matters a lot in terms of how much rainfall and when does it come. We're seeing a shift where we used to have really dry falls, and it would remain dry until maybe February, but it would be cold, would get snow and stuff like that, and then would get rain in the spring, and it was all nice and orderly. Now we get rain in the fall, quite a lot of it. We get, you know, it will go down rapidly, you know, we'll get these big freezes, go to minus something, then it'll pop back up to 50 and start raining again. and for the past probably 6 or 7 years now, I have a crew lined up every Christmas and New Year's to sample. I didn't have to worry about that previously. Now, there's somebody who has agreed to schlep out and get samples on Christmas and New Year's.
And does any of this field have like tile drain? Did you see the tile drain effects of the?
So they're all, I'm sorry, I didn't explain the entire system, but we're looking at plots that are individually tiled and routed to a hut. They flow through a large in-ground lysimeter that has clay walls down to glacial till. And the plots are about 30 feet, 10 meters wide, 180 feet long, and it's the center of the plots where you have these lysimeter boxes, and you have twin drains. One is perforated in the lysimeter and blind outside. The other is perforated outside, blind inside. The outside perforated one goes to the ditch, and the other one goes to the hut. And then we measure the flow and do the concentration.
We've got 2 online. So this is from, let's see, Azucena. What strategic approach do you recommend for shifting the research focus away from the highly unstable measurement of carbon in soil, particularly given its significant variability across different scales and spatial distributions? Or how do you see this moving at different directions?
Well, we were having this conversation earlier about, there are things that we do that may increase carbon, but they have other benefits.
Mhm.
Some of them are easy to measure. Some of them are much less easy to measure. So having a cover crop may or may not do too much for your soil carbon, but it sure keeps cover on the ground in the wintertime and does that pretty well. I think, there are places in the world that are highly eroded where the soil carbon is really low and there's a lot of opportunity to increase it. But again, the most important thing is probably to keep the soil there and rather than having it move off. Soil carbon, it's good, right? It's a fine thing. It's just that it's hard to measure, and we've gone way, into we're going to measure it everywhere all the time, all at once.
Mhm.
And it's going to tell us something that we want to pay people for. And I think that's incredibly problematic. If you're just doing it, and this is where I've been looking at just the loss on ignition organic matter measurements. That's a cheap one that we have. I don't know how many percent organic matter measurements are out there in farmer soil test reports, and they go way back. And they've got some of the same variability, but where I've looked, and again, I haven't looked everywhere, but there are not a whole lot of direct comparisons. That's a metric that's a proxy that kind of tracks it. I think it really depends. We need to sit back and think about what's our objective, right? Is it to help people adapt to climate change, or is it to solve all of our problems in the context of our commitments to climate mitigation via soils? I think that's been a huge challenge. It's been helpful. It's got people to like soils, which is good. Everybody feels warm and fuzzy about soil now. But then to think about, we have to monitor this. I don't have a good answer because if we had a good, reliable, easy measurement, everybody would be doing it. And we don't. The book for measuring methods in soil organic matter is like this thick. There are many different ways to measure it. Now we've all settled we're going to do it this way. Loss on ignition, soil seed concentration. Maybe we'll do a few other additional. We'll do mineralization studies and that kind of thing. In the end, we're not even sure, in absence of comparatives, how much that tells us about whether a system is healthy or not. A younger soil has more carbon. A soil up here has more carbon than soil down in Texas. You're not going to be able to sequester much carbon in Texas with minerals and mineralization and that kind of thing. So I think I think we need to think about what is the objective? And then what's the way to go about incentivizing the objective?
Yeah, one more. They said, great presentation. Your comments about insufficient resources allocated to data resonate. Could you offer us researchers a couple of concrete suggestions how to deal with the current situation?
Okay, well, if you don't know it, your libraries and your Minnesota repository, I think has some, can provide some assistance. What we're beginning to see, budget for it. And one of the big challenges that people like, I don't know how to budget for it. Well, put in more money than you think. Because, think about your workflows and think about the time it takes to manage that data, to get it into the shape that it needs to be. And, there's you can hire, probably an undergraduate from your engineering programs or whatever to write you some code. But then, you're not necessarily guaranteed that anybody else can run that code, or that that code will be useful in the context of other people and give you a really robust workflow for your data. So I think the first thing we have to do is ask for the money for data, which means sacrificing it from something else, which we really hate to do. And so far, we've seemed to think it's kind of free and easy to do. But with the reporting requirements that are coming up with grants now, it's not, if they have any teeth in them, we will be reporting our data. But many, like we now have a data services in our ag, find those people, talk to those people. It's not a problem I think most researchers can solve for themselves, unless they have a whole lot of time on their hands.
Other questions? All right, well, let's thank our speaker again.